Hi everybody. We're now starting a new chapter, chapter 11, series solutions to linear differential equations. And our first section is going to be a review of power series. Everything that we talk about here, we've learned previously. There are a few new definitions, but most of it is going to be things we've already seen in Calculus 2. So we now review facts about series from Calculus 2. Needed for later. And let's begin with a definition. A power series centered at x equals x naught is an infinite series of the form sigma n equals 0 to infinity of a n x minus x naught to the n, where a n are constants for all n, and x naught is also a constant. Okay. Now, the most common thing that you'll be seeing is a series centered at 0. Sorry, it should say power series, really. We're not talking about regular series here, we're talking about power series. So a power series centered at 0, which looks like this. Okay. Why do we focus on this? Well, the main reason is this note that we're about to write here. We can actually shift a power series. So any power series centered at x equals x naught to one that is centered at 0 by letting u equal x minus x naught. In other words, this is basically a translation. We can basically take any power series and just shift it over. So we mostly focus on those with center 0. And these are ones that look like star above. Okay. So we need a definition here. What does it mean for a power series to converge at a number? So a power series star is said to converge at x equals x1 if plugging in x1 makes it converge. So what's that going to look like? It looks like this. Instead of x to the n, it's going to be x1 to the n. Okay, so you actually plug the number in for x if this guy converges. And what does it mean for a series to converge? This means that the limit as k goes to infinity of n equals 0 to k of a n x1 to the n exists. When I say exists, remember, I mean as a real number, okay? I don't mean equals infinity, because remember, that means that a limit does not exist. Okay, so let's keep going with another definition. What is the interval of convergence of a power series? So the interval of convergence, which we abbreviate IOC, of a power series is the set of all x for which it converges. Set of all x for which it converges. So another way to think about it is it's the domain, right? The domain of a power series. So we need one of the most important theorems regarding series that we learned in calculus. So in this section, we call it the basic convergence theorem. Basic convergence theorem. So given a power series, and by the way, when I write a power series like this and I leave out the n equals 0 to infinity, understand that it's there and we're just leaving it off just for the sake of brevity, okay? It's really there, but we don't have to write it every time if we're not actually going to be doing any calculations with it, okay? So given a power series, exactly one of the following is true. So there are exactly 3 cases. So first, the power series converges only at x equals 0, which remember means its center. Okay, so that's the first case. The second case, the power series converges for all real x or the third case, which is the most interesting case, there exists some positive real number, we call it capital R, and it needs to be finite, it can't be infinity, such that the power series converges whenever the absolute value of x is less than r and diverges for the absolute value of x is greater than r. And just to remind everybody what this means, this really means when x is between negative r and r, and this really means x is bigger than r or x is less than negative r, right? That's what those two things mean. So these are the only three possibilities. Hopefully we remember this from calculus. So we have a special name for this capital R. Let's give a definition here. We call this number R in case 3 the radius of convergence. Which we abbreviate ROC of the power series. Okay. And in particular, we also want to have a radius of convergence for the first two cases as well. So if the power series only converges at x equals 0, so in other words, in case 1, we define R to be 0. And in case 2, we define R to be infinity. Okay? So something important to note here. In case 3, the series may or may not converge at the edges when the absolute value of x is exactly equal to r. You'll notice that there is no, we talked about x, absolute value of x being less than r and absolute value of x being greater than r, but we never talked about the absolute value of x being equal to r. And what does that actually mean? That means that x is equal to plus or minus r, right? So in those cases, we don't know whether or not it converges. So we must test the edges separately. Okay, so if we were to draw a picture of what we're talking about, it looks like the following, right? We're talking about, so in other words, if this is case 3, and this is x equals 0, and this is x equals r, and this is x equals negative r, I want you guys to imagine that we converge everywhere along here. This is where it converges. And over here is where we get divergence. And on the edges themselves, we don't know. Okay, on the edges themselves, we have to test separately. Now, we learned a lot of tests in calculus, and then we're not going to review all the tests here, but there is one test that I want us to review only because it's how we're going to determine the radius of convergence. So I want you guys to recall the most important test regarding power series is the ratio test. So the ratio test allows us to determine which case we are in and helps us find the radius of convergence. So just to remind you of the test, so for a power series, a n x to the n, what we do is we take the limit as n goes to infinity of a n plus 1 divided by a n, and we do the absolute value of that. And if that limit equals L, then so there are three possibilities. If the limit is infinity, then the ROC is 0, and we are indeed in case 1. If the limit is 0, then that means it converges everywhere, so the radius of convergence is infinity, and we are in case 2. And finally, if the limit is a positive real number, then the ROC is actually equal to the reciprocal of L, and we are in case 3. Okay. So, as a quick example, let's find the radius of convergence of the following power series. So, determine the radius of convergence of n squared x to the n over 3 to the n, and we're going from 0 to infinity. So we are going to do the ratio test. We're going to do the limit as n goes to infinity of the absolute value of an plus 1 divided by an. Okay? So what do we end up with here? We end up with so an plus 1, that's going to be n plus 1 squared over 3 to the n plus 1 times, the reason I'm doing times here is because dividing by an is the same as multiplying by the reciprocal of an. So this is going to be 3 to the n over n squared. This is what we're going to divide. And you may wonder what happened to the x's. Well, in this class, if you look back here, you notice that the an's do not include. An is just the coefficient in front of the x to the n, and so that means this part is not going to have any x's in it, okay? Okay, so what do we get here? What is this equal to? Well, I'm going to do some cancellation here. I know 3 to the n cancels with all the 3's except for 1, and that's going to look like this. We end up with the limit as n goes to infinity. The top is n plus 1 squared, and the bottom is 3n squared. And I'm going to divide top and bottom by n squared to take this limit. This is going to equal 1 plus 1 over n squared because it becomes an n when you divide it by it since it's inside a square. And over here we get a 3. And so this guy goes to 0. So our answer is just going to be 1/3. This guy is L, which means that the ROC is equal to 1 over L, which is 1 over 1/3, which is 3. So the radius of convergence is 3. In other words, we know that we converge when x is between -3 and 3. Now, we don't know whether or not it converges at 3 and -3. Those would have to be tested separately, but we don't have to do that now because the problem just asked us to figure out whether or not, or to figure out what the radius of convergence was. So we're done with that. Hopefully you remember doing this in Calculus 2 and it doesn't feel too out of left field here. Just a review. So let's continue on with our review. Let's talk about the algebra of power series. The algebra of power series. So fact. The only way that a power series can ever equal 0 identically, this can only happen if and only if all of the coefficients are exactly 0 for all n. Let me make this a little more clear for all n. There we go. We're going to be using this fact a lot, okay? So remember this. If a power series is equal to 0, that can only happen if all of the coefficients are 0. So let's keep going here. What are some properties? So I want us to let f of x equal to a n x to the n and g of x equal to a different series, b n x to the n. Let these guys be power series with radius of convergence equal to r1 and r2 respectively. Then we have the following 3 facts. So first of all, how do we add 2 power series together? You can add 2 power series by combining like terms. So let me actually make these go from 0 to infinity up here. So if you add these 2 together, you can do that, and you end up with combining like terms, and that means you add the coefficients that correspond to one another. So we have that, that's how you sum. Also, if you multiply a series by a constant, you end up just multiplying the coefficients by the constant as well, which is basically the distributive property, right? This is like the same thing that if you do c times x plus 5x squared, you end up with cx plus 5cx squared, right? So it's the same idea. Okay. Third fact. This one's a little trickier to conceptualize, but this is how you multiply 2 power series. When you multiply 2 power series, you end up with a new Cn, and the way that you get Cn is you add together all possibilities of the following products. This is basically using FOIL, right? This is basically using FOIL when you multiply. Make sure that everything gets multiplied by everything, and then the ones that correspond to one another are given here. And you are not going to have to do this often, which is why I won't elaborate too much on this formula. The important part are the first two: how you multiply and how you add. And of course, that gives you subtraction as well, right? It's also worth noting that if you have these two radius of convergence, R1 and R2, we should also note that the above series all have radii of convergence. So if one series has a radius of convergence R1 and the other series has a radius of convergence R2, then when you add the two series together, they all are going to have radius of convergence equal to R, which is going to be the minimum of the two. Whatever is the smaller of the two numbers, that becomes the radius of convergence. Now, something I want to point out here, only because your book doesn't mention it, but we do it a lot, useful trick when combining series, is called reindexing. Reindexing means that at any point you are allowed to take a series and you're allowed to shift the starting point. But if you shift it down, then that means you have to add 1 to n. Okay? Or if you shift it up from the original, then that means that you have to subtract 1 from n. And if you plug in n equals 2 to all of these, you can see that if you plug in the starting value for all of these, you can see that the first term is f of 1 for all three of these, right? Even though it looks a little different inside. This is a very useful trick that you're going to see us do a lot. So let's go ahead and try an example, and we are going to be using this trick. So example. Assume that the coefficients in the expansion satisfy the following relation. The directions now say express all an in terms of a naught or a0, right? So we are going to be looking at this relationship here. This is a way, this equation gives us a way to relate the terms together. And this example is really important because this is the general technique that we're going to be using in the next section in order to solve differential equations using series. So pay close attention to how this problem is solved. Okay, so we need to take this guy that we just wrote down. We need to take this guy and we need to figure out a way to write that as a single series. Now, what's the problem that we notice? The problem that we notice is that the one on the right is x to the n plus 1, but the one over here is x to the n. We can't combine the two series yet because we would like for the powers to match. So how can we do that? We can accomplish this by re-indexing. Okay, what I would recommend is re-indexing this left guy. It doesn't actually matter which way you choose, but here's what I'm going to do. This guy right here, we want that to be what? So actually, yeah, there's so many ways of doing this. I'm going to take back what I just said here. If we want it to remain x to the n, then the one on the left is okay, but the one on the right is an n plus 1. So we want this guy to become an n, right? So if we want to turn that into an n, we want to make all the n's smaller inside the sum. That means we have to make the n's bigger in the index to compensate. And so what we can do is the first sum remains the same. But the second sum is going to go from now 1 to infinity, but we now get to subtract 1 from all the n's inside. So this is going to become a n minus 1 times x to the n. And that's going to equal 0. So this was, we re-indexed, so re-indexing. Remember I mentioned that trick? Very useful. Now what? Well, now we can combine like terms, can't we? Because we notice that the powers match, right? We've got n and n. So we know based on this property, let's come back up here. Based on this property, property 1, we know that we can now add or subtract power series together by just adding or subtracting their coefficients. So what's this going to look like? This is now going to be the following. We're going to write n minus a n minus 1 times x to the n, and that guy equals 0. So I've now combined the two power series together, and now we're going to use the fact. Let's come up here. We're going to use this fact now. We know that the only way a power series can equal 0 is if and only if all of the coefficients are 0. So we're going to apply that to this power series now. This gives us n minus a n minus 1 is equal to 0, which means that n is equal to a n minus 1, which is the same as saying that a n is equal to 1 over n a n minus 1. Okay, so what does this mean? This means that a1 is going to be 1 over n a0, and a2 is going to be 1 over n times 1 over n a0, which is 1 over n squared a0. A3 is 1 over n times 1 over n squared a0, which is 1 over n cubed a0. And now I hope it's clear to everybody the pattern, right? We found a way to write all of the a's in terms of a naught. And hopefully you could see the pattern. It seems like an is always 1 over n to that power. So if we keep going, I don't want to use n here because we're already using n. Oh, you know what? I wrote 1 over, I'm sorry, I made a little mistake here. I wrote 1 over n before, but remember that n is not a dummy variable here. N corresponds to which one we're talking about here. So I made a little mistake here. Let me fix this. Let me do this again. Starting with A1. The A1 is going to be 1 over 1 A0, which is just A0. A2 is going to be 1 over 2 A1, which is 1 over 2 A0. So yeah, the pattern is a little more complicated. What's A3? A3 is 1 over 3 A2, which is 1 over 3 times 1 over 2 A0. Let's go one more, and I think you guys are going to see the pattern here. A4 is equal to 1 over 4 times what we have before. I hope we can see what's going on here. It seems like we keep getting a factorial, don't we, right? The first one is 1 over 2 factorial A0. This guy is 1 over 3 factorial A0. This guy is 1 over 4 factorial A0. And so the pattern is clear. This means that AN is going to equal 1 over n factorial times A0. Okay. So this means that our power series is really equal to this, which, by the way, is the same as, we could pull the A naught out, it's just a constant. And so really we end up with this. Okay. This is the relationship that we needed, though, and that's what allowed us to write down what we just did. Okay. What is so nice about power series is how easy they are to differentiate. So our next topic of review here is going to be differentiation of power series. So suppose f of x is equal to the following series. And let's say that this guy has an ROC of R. When you have a power series, guess what? You are allowed to differentiate it as many times as you want. Then f of x can be differentiated an arbitrary number of times and keeps the same ROC of R. So how do you actually take the derivative? We can use the power rule. So how does the power rule work again? What would the derivative f prime of x be? Well, because the powers are given by n, the derivative is just going to be what you get when you pull n down, and then x is going to be to the n minus 1. Okay. What would f double prime of x be? You can just do it again, right? You could take the power, you can use the power rule as many times as you want. So now you're going to take the derivative of the derivative, and so the n minus 1 comes down, and so you have x to the n minus 2. And we can just keep doing this. All right, so if you wanted to take 10 derivatives, you could do that. Just keep pulling the n's down. Now, one thing I want to note here is that oftentimes we will not really re-index, but we'll start the series at the first relevant point, because when n is equal to 0, of course, that term is going to make the whole thing 0. And so there's no point in starting it from n equals 0. We can actually start this from n equals 1 without losing anything. Here, we can start it from n equals 2. Right? Because notice that if you plug in n equals 0 into this one, that makes it 0. And if we plug in n equals 1 into that one, that makes it 0 also. So the first two terms go away. Okay. Oh, why did I write n minus 1 here? This should be n minus 2. So sorry about that. We did not reindex. All we did is we threw out the 0 terms, okay? Which we're going to be doing quite often. Right? There's no point in writing something down if it gives you a 0 anyway. All right, so this is the use of the power rule. Next, we have a definition. This is a new definition. We did not learn this definition in calculus. A function is said to be analytic at x equals x naught if it has a power series representation which, by the way, sometimes I will abbreviate power series representation like this, PSR. So just to remind you of that, power series representation which converges using x equals x naught as its center. With ROC not equal to 0. That's an important fact. So sorry, that's all one sentence. Okay. So what this means is that if you converge, if the power series converges using the center of that point, and it does not have a radius of convergence equal to 0 there, then we call the function to be analytic at that point. So, something we do learn in calculus. Every function, analytic, at x equals x naught can be uniquely represented by a power series. Centered at x equals x naught, and we call it a Taylor series. And just to remind you of the Taylor series formula, oops. It looks like this. Nth derivative of f at x naught divided by n factorial times x minus x naught to the power of n. Of course, the one that we use more often is when we have center 0. If the center is 0, we call it a Mclaren series. Oops, no dash. Mclaren series. A few well-known Mclaren series from calculus include, so some famous ones are e to the x, which is 1 over n factorial x to the n, sine of x, which is negative 1 to the n over 2n plus 1 factorial x to the 2n plus 1. Cosine of x, which is n equals 0 to infinity, negative 1 to the n over 2n factorial x to the 2n. The way I remember these is the fact that sine and cosine, so sine is an odd function, cosine is an even function, and that's how they have the odd and even terms there. These are all from calculus, okay? There are, of course, a lot more, but you don't need to memorize these, okay? I'm just reminding you. But something to note here from this example that we got up here, this means that the series that we were talking about is actually a naught e to the x, isn't it? Because this guy is exactly the Taylor series for e to the x. So that's pretty interesting. Okay. Let's keep going here. I know this is long, but we're doing a lot of reviewing from calculus, right? This is a lot of what we learned in the series chapter for calculus. So theorem. If f of x and g of x are analytic at x equal x naught, then so are the following. First, f of x plus or minus g of x. Also f of x times g of x. And also f of x divided by g of x, provided g of x is not 0. So a good question you might ask is, what would, so let me write it this way. What are the radii of convergence for the above? So in order to answer this question, we do need a theorem. This theorem is mainly going to apply to this last case, because that's when things get a little tricky, right? When you're dividing by something. So let's look at the following theorem. If p of x and q of x are polynomials and q of x naught is not 0, then the power series representation of p of x over q of x has ROC equal to R, where R is the distance in the complex plane from x naught to the nearest root of the denominator. So recall, and we're going to do a couple of examples of this using this theorem, so it should become clear, but I want us to recall the distance formula, okay? Recall the distance formula. The distance between two complex numbers. Now, I know you've probably never thought about how you take the distance from two complex numbers to each other, but actually it's the same thing as finding the distance of 2 points in R2, okay? Because it's the complex plane. And so this is just going to be the square root of a minus c squared plus, and then b minus d squared. This would be the same thing. So just to give you guys a visual here, if this is the real axis and this is the imaginary axis, if this point is a plus bi, then remember this is a and this is b. And if this guy is c plus di, then that means this is c and that's d. And so all you're really doing is finding this distance right here. And that's just given by the distance formula, right? You can think of this as being the point A comma B, and this is the point C comma D. That's how you treat it geometrically when you're graphing complex numbers, okay? So don't think too hard about this, okay? I want you to remember that a real number, like whatever number you get, let's just call it A, is really A plus 0i, and so when you graph it on the complex plane, it looks like A comma 0. So keep that in mind when you're finding distances. Okay, remember, real numbers always have imaginary part equal to 0. So I want us to do a couple of examples here using the following, or using the previous theorem, okay? So example, let's let f of x equal to 1 minus x over x squared minus 4. I want us to determine the ROC of the power series representation centered at, so first part we're going to do is x equals 0, and second part we're going to do is x equals 1. Okay. So let's start by factoring the denominator of f of x, which is going to be x plus 2 times x minus 2, right? So that tells us, if you recall our theorem says to find the radius of convergence, we need to find the distance. I'm going to underline in red here. We need to find the distance in the complex plane from x naught to the nearest root of q of x. You may wonder how we know which one the nearest root is. Sometimes it's obvious, but it won't be obvious if they're complex numbers, okay? So for now, though, it should be obvious. Okay, so we know that the values to check, so I'll say q of x, remember q of x is the denominator, right? q of x. q of x is 0 at x equals plus or minus 2. So these are the values that we have to pick. These are the, these are the values that we have to check, right? And so what are we going to do? So for part A, we're going to start by taking the distance. What's the distance from 0 to 2? It's just 2. What's the distance from 0 to negative 2? It's also just 2. Now, if you're confused by that, remember, the second guy, for example, is 0 plus 0i and negative 2 plus 0i. And that's going to equal the square root of 0 plus 2 squared plus 0 plus 0 squared, which is just 2, okay? But again, we can use a picture. Here's what we're looking at here, okay? We're talking about the center of x equals 0. We have a 2 and we have a negative 2. And notice that the distance is 2 in either direction, right? And so this means that the ROC is just going to be 2, because 2 is the smaller between 2 and 2. They're the same distance away. In other words, we're on the real axis. We don't even have to use the imaginary axis, right? That's the real axis, that's the imaginary axis, but we were talking about points that were all on the real axis here. So there was nothing We don't have to even use the distance formula. We can just count the number of spaces away, okay? Let's look at part B. Now, we're talking about x equals 1. And so the distance from 1 to 2 is 1. And the distance from 1 to negative 2 is, of course, 3. So that means the ROC would be 1, right? Because that is the minimum of the distances from, or the minimum of the two distances, right? The minimum of 1 to 3. Okay, let's do another example. This one will be more interesting because it will utilize some complex numbers. So I want us to let f of x equal 1 minus x over x squared plus 2x plus 2 times x minus 2. And I want us to determine the ROC of the PSR of f of x centered at x equals 0. Okay, so we should notice if we try to figure out where q of x is equal to 0 here, we're going to need to use the quadratic formula, right, to figure out when this guy is 0. So this is going to be x equals negative 2 plus or minus the square root of b squared minus 4ac all over 2a, which is negative 2 plus or minus, let's see, square root of negative 4, which is 2i over 2, which is negative 1 plus or minus I, right? And also, we have x equals 2 from the other factor here, right? From this guy. So we also have x equals 2. And so we have that q of x equals 0 at x equals 2 and negative 1 plus I and negative 1 minus I. So there are actually 3 different distances that we're going to have to check. And so if we were to graph these all on the complex plane, remember this is the real axis, and this guy is the imaginary axis. We're centering at x equals 0, so here is x equals 0, and then all of these guys, let's see where they sit. We have x equals 2 is right here. We have negative 1 plus I is right here. And then we have negative 1 minus I is right here. And so we're going to need to find all of these distances. And I think you guys can tell what's going to happen, right? So let's start by finding, remember, this is 0, this is 2, this is negative 1 plus I, this is negative 1 minus I, okay? Those are the points that we're looking at. So let's start by finding the distance from 0 to 2. I hope we can all tell that that's just 2, right? This distance is 2. Now, what about this distance right here? That distance, the distance from 0 to negative 1 plus I, remember guys, that's the same as the point negative 1, 1, and we're finding that distance. So that's just going to be the square root of 0 plus 1 squared plus 0 minus 1 squared, which is just the square root of 2, right? Again, it's just the distance formula, okay? So this is the square root of 2, and this guy, we know it's going to be the same thing here. The distance from 0 to -1 minus I, just from looking at the picture, we can tell it's going to be the same, but it's okay. We can just use the formula again. We end up with 0 plus 1 squared plus, and then this is going to be 0 plus 1 squared. Again, that actually ends up not mattering. We end up getting a square root of 2 for both. So the minimum of all three of these distances, oops, not 0. The minimum of 2, square root of 2, and square root of 2 is just the square root of 2. So this means that the ROC is the square root of 2. And again, that's for the power series of this original function f of x, of this guy right here, centered at 0, okay? So in a way, what we're doing is we're figuring out how far away that center is from the bad points, right? These are the bad points. Bad, bad, and bad. We're figuring out how far away our center is, and this is our center, right? We're figuring out how far away the center is from the bad points, and whatever that smallest distance is, we call that the radius of convergence, because if you think about it, that means that we can sort of think of it as we can create a circle around it with that radius, and we won't hit any of the bad points, right? That is as far out as we can go. All right, everybody, that is it for this section. Thank you so much for watching.